And all this means is, right, B has to be better, or B has to be worse than C to some extent, right? But if I didn't have this term, B could equal C, and I don't want that to be true. So if this term has a negative really small number, and if I make this a really small number, now it can equal 0, but I'm at least guaranteeing that B is at least a little bit worse than C. All right. Have I showed you guys how to use the Excel solver before? Some of you in optimization. I thought I brought it up. Okay. So Excel has a way of doing optimization where it's magic, right? You just set it up and you say, go Excel, go, and poof, optimization happens. And you don't really need to know what's going on behind the scenes. And that's pretty nice. Probably what's going to happen, though, is it's not going to be there, right? So it lives in the data tab. It's called Solver. Probably when you open up your version of Excel, it's not going to be there. It's an easy add-in. What you do is you go to File, you go to Options, you go to Add-ins, and then down here it says Manage Excel Add-ins, and you hit Go. And it's going to bring up this thing. So you just say, I want the Solver add-in. You click it, you hit OK, it thinks for a second, and now it shows up. Right? So now you have access to the Excel Solver, which is basically the Excel optimization tool. When you click on Solver, let's delete all of this. Oops. When you open it, it's going to look like that, right? Empty sheet. You're not going to have anything. So the first question is, it says set objective. All right. So what we need to do is we need to build an objective function. So that's what I have over here, right? So my objective function, we said for HEIM, is that we want to take the sum of the, so 1 minus the sum of the weights squared. And we want to minimize that. Right, so in this case, I have 1 minus the sum of G2, G3, G4, which are my 4 weights, or my 3 weights. Right now you see that they're at 1, so it's going to be 1 minus 3, which is 2 squared, right? So my objective is equal to 4. So that's the objective function that I want to try to minimize. I've defined my delta value as 0.001. And now what we can do is we can build these constraints. So it's actually going to be a pretty easy change. I'm just going to say this is no longer true, and it's now 26.
Why don't we have the weight constraint? The sum of weights is 1. The sum of our weights has to equal.
We essentially, that's kind of what we're doing. We're just setting it as an objective.
So we get built in on that.
Because if the sum of your weights don't equal 1, if it's 1 minus the sum of your weights, right?
So once it gets close to 0.
It's got it, yeah. The optimization is going to try to get as close to 0 as it can. So it's automatically built. Yeah, so that equality constraint, that W1 plus W2 plus W3 equals 1, we've actually just wrapped up into our objective function. Okay, so what I had here originally was E15, which was B minus E16 plus G, because I want to get this form to go with these values. So we're just going to delete these values. So this doesn't exist anymore. I'm going to move this down. Right. So what we want to say for this constraint is I want B minus C plus delta. So B is going to be E25 minus C plus delta. Right? So that's my constraint there. Then I want to say, for this one, it's going to be A minus B plus delta. So A minus B plus delta. Okay, so E minus F, E minus F plus delta. So now I want to do D minus E. So D B minus E plus delta. I minus G plus delta. And then H minus I plus delta. Right?
You would give us those preference rankings?
You can make them up on your own. So this is for you, right? So in a homework, what you would be responsible for would be picking values of P. I don't care what you pick, right? Make it between 0 and 100. That's your constraint. As long as it's between 0 and 100, I don't really care, right? And I'll give you the hypothetical alternatives. All you want to do is you want to choose them however you see it. Yeah.
When we talked about this in class, we chose 3 instead of 2. I know that doesn't matter, but we thought we had to go through all of them. So we had 9, we had to do 3 sets of 3. On this, you're not doing pairs of 2. Does it really matter? Does it have enough?
You want to have enough constraints so that you have enough degrees of freedom to solve for it. So you don't need all of them. Because, like, if you say C is better than B and B is better than A, you're implying that C is greater than A already. So you don't need that one.
Okay.
Right? It would be another, if C is greater than B and B is greater than A, then by definition C is greater than A. And I don't need to worry about it. So yeah, you can get 3 constraints out of it, but you really just need the 2 that give you the full piece of information. You could put it in. It's not going to change the answer. It's just more work of setting it up.
But you do have to have some comparison for every hypothetical.
Yeah.
You can't move one out.
Right. Don't leave any out.
So everything's involved in some.
Yep. So we'll go back to solver. So our objective is going to be this objective cell. We want to, you can either maximize it, minimize it, or set it to a value of, right? In this case, we can minimize it because the idea of making it that square term was that the smallest value is going to be when the sum of the weights is equal to 1, so that's okay. By changing the variable cells, that essentially means what are your design variables? Like, if Excel's going to go in and change stuff, what can it change to make this optimization happen? Well, we want to solve for the weights, right? So I want you to change the value of my weights in such a way that I get what I want. So we're going to do that. Okay, so now constraints, right? So we're going to add a constraint that all of these cells, right, all of these G's are going to be less than or equal to 0. Right, so we're going to add that. What other constraints might I want to put on this problem? Don't need that one. Okay, so the weights can't be negative. That's a good one. So all of these weights have to be greater than or equal to 0. What's the other one?
Or less than 1.
Yep, good. So all of the weights have to be less than or equal to 1. All right, so now I've constrained my weights to live between 0 and 1, and all those constraint equations have to be less than or equal to 0. So as long as that happens, I have a weighting structure that works. So now we hit solve. And it turns out, for this case, that actually weights of 1/3, 1/3, 1/3 are a viable solution. All right? So it is what it is. If we look at that, right, so these weight values are tied back to this original problem sheet. So 1/3, 1/3, 1/3. If we looked at the score of these designs, what do we see wins? We see that the A340 wins. Right, because how I calculated the score is it's B16. Right, so when we built these strength of preference numbers, so it's the strength of preference for speed times the weight, plus 100 times the weight, plus 18 times the weight. So when we look at this, A340 is the winning aircraft. Now, what we also said was that that might not always be true. or there's multiple solutions that could hold for this problem, right? So we could go in and manually explore some of those. Maybe 0.25, 0.5, 0.25. No, that doesn't work, right? All my weights equal 1, but if you look at the constraints, I'm close, but F isn't better than E. So that sucks. But I can give it a different starting point, right? Off of that different starting point, what we see is that now it goes to a different set of weights, right? All those constraints are satisfied. The objective is still equal to 0, so we have a viable solution. If we go back over to the original problem, well, we see that the A340 wins again, right? But this time, you know, you see these two are kind of close to each other, so the A340 wins. Maybe we could go 0, 0, 1. So that gives us a different set of weights. A340 still wins. Maybe we try 1, 0, 0. Ooh, the 747 got closer this time, right? So maybe we could try 0, 1, 0. Back to the A340 kicking butt. Right, so this would just be the kind of, now that you've gone through the process, now you're just kind of exploring your solution, right? So what do we learn about the overall robustness of the A340? In the few cases that we started with, right, we gave it some starting points. It won all the time. Does it mean that it's always going to win? Not necessarily, right? When we saw that the 747 was starting to sneak in, maybe there's probably a combination of weights that would exist so that that's true. Do we want to find one? Yeah.